All right, so lesson 4.1, patterns and equations. So what we're going to be doing in this one is talking about how we are going to use expressions and equations to describe some patterns. So this is really the beginning of setting up equations, and the reason why we use equations in everyday life, right? Like they come up like a ton. Like when we start doing physics and we start doing science, we use these equations to solve for things, right? It's through these different patterns and these equations. Like this is how we end up sending people to the moon and building computers and all these things, right? So much of it is based on equations, and this is kind of like the beginning of setting up these equations, right? And the way we make equations is by first looking for a pattern. Okay, so let's look at a pattern here. So if I'm looking at this example, it says if ordered pairs are used to represent data obtained from real life, then they actually represent a specific pattern of observations. So if we look at this example, say a landscape designer uses wooden boards as edging for the plots of a herb garden. Okay, so this is our example. Now it says from this pattern, can we use this pattern to predict how many boards will be required for any number of plots? You know, so let's say if you wanted to know how many boards you would need, right? So a board would be, you know, there, right? So in that case, you'd have 4 on the first plot. And on the second plot, you would have, well, those 4, and then 1, 2, 3, right? And then on the next one, and it goes up like that, right? And the reason why this will be useful to turn this into an equation at some point is because what if I asked you how many boards we're going to need if we make 56 plots? Right? Like, that's going to get ridiculous. You're not going to want to draw out 56 plots and then actually count all the boards. But we can math this thing. We can set up an equation to describe it, right? So let's see if we can figure out what pattern is actually happening here. So if you look at plot number 1, like I said above, there's 4, right? There's 4 sides to that square. So then you'd start off by saying there's 4, right? There's going to be 4 for the first plot. The second plot, there's going to be those 4 and then 3 more, right? So there's going to be 7. The next one, you'd say, okay, well, now we're going to have those 4. Sorry, my bad. There was, yeah, those 4. Yeah, sorry. And then from there, you're going to say you have those 7 and then 3 more. So now 10, right? And now you have those 10 and then 3 more. So now you have 13. Can you guys see that pattern that's happening? Like I wrote it down here so you definitely can see it. But do you see how every time we go up, right? So plot 1, plot 2, plot 3, plot 4, the number of boards we need are going up by 3 every time, right? So that's our first piece to this pattern here. So if we scroll down a little bit, then let's look at this example now, just while we're looking at that. So consider the following table of values representing the height in meters of a building with a given number of levels. So if we're at level 1 and then it has a height of 60, and then level 2 is 120 and 3 is 180, can you guys see the pattern? What is this going up by? Can anyone tell me?
60.
Yeah, it's going up by 60 every time, right? So it goes up by 60, and then it goes up by 60. So here, what I'm going to do is I'm going to make it so you guys can try to put it or answer the question. Okay, so I'm just going to pause the video part. Okay, didn't push record, but the answer there was 300 if you're just watching the video. Okay, so now can you guys make sure you turn back to the Google Meet here so you can see my screen? So now looking at this one, like again with our herb garden example, let's describe what's actually happening here. Like if we know how many plots we have, how can we use that to figure out the number of boards that we're dealing with, right? Well, what I'm going to do, let's say I'll tell you the answer and tell you where we get that in a second. So you can see that the answer for the number of boards that we'll need, so the number of boards, is going to be, we'll say B for boards, is going to be equal to 3 times the number of plots, so 3p, right? When you write beside, you mean times. And then plus 1, right? So that's what the answer is. So let's just try it out to prove that this actually will work, right? So if I want to know how many boards I need, this one, right? This is my B and this is my P. So if I want to know, like, let's say for this one, if I want to know if I have 2 plots, that'll equal 7. Let's try it out. We could say, okay, the number of boards would equal, and then that would be 3 times, and instead of a P, I'm going to put in what P is, right? I'm going to say there's 2 plots. So 2 plus 1. Okay, well, B is equal to 3 times 2 is 6 plus 1. So then B is equal to 7. And yeah, that's true, isn't it? It's equal to 7. I'm going to do it one more time just to prove that this actually works, right? So this is the equation that we want. So let's say we were doing it for this one. Let's say the number of plots was 4. So then we'd write B is equal to, here I'll write the equation again, it was 3p plus 1. So then B is equal to 3 times, and I'll put 4 in this time, that's my input, is 4 plus 1. Okay, so B is equal to 3 times 4 is 12, and then plus 1. So that's going to be B is equal to 13. All right, so I think I've probably convinced you that this is the equation, but how did we get there? Well, do you guys have any, like, let's just look closer at this. So now I'm looking at this one. Do we see any numbers showing up here, right? So this was going up by 3, right, every time. Do you guys see the 3 in this equation, right? That'll always be the case. So if the thing is going up by 3, that's like the multiplying factor, right? So you're going to be like, it'd be 1 times 3, 2 times 3, 3 times 3. But the amount that it goes up by here will always be that part right there. Okay? And then, but the second part of this is, where did we get this 1 from? Okay, well, let's think for a minute. The 1 is it's like our constant term, right? We have 1 board no matter what. Okay? So we can think of it this way, right? So if we went back 1, like the number of plots, if I went to 0 on this pattern, like went 1 backwards, what if I went like 3 this way, right? So instead of counting up by 3, we went down. Can you see if we went back to 0 that now we have 1, right? Because 1 is like our starting position. That's where we start from to begin with. So you'll always be able to do that. This number here would always be, if our x value here, like our input, was 0. That's going to be our 1. Okay? How you guys doing with that? Can you guys tell me if that made sense?
Yeah.
Yeah?
You lost me on the 1.
Yeah, me.
Lost. Okay. Sounds good.
Yeah, I got lost too.
Let's do that. Yeah, I knew it would. So, okay. Let's go over that again. So, you know what? I'm going to make another another table here just to kind of give you a new example. So let's say we had, this was like my x and that was my y instead of p's and b's, right? So if I said, we got plot or whatever, it'd be like 1, 2, 3, 4. And on this side, I've got 6, 8, 10, and 12. All right, so, and we want to make an equation out of this thing. So what we're going to do is I'll say, okay, what does this thing go up by? What do my y's go up by every time?
2.
It goes up by 2. So I know that this thing is going to be y is equal to 2x. And then I just have to figure out the plus or minus part of it, like plus something or minus something. And what this number will always be is if I go 1 backwards. Can you guys see if I went 1 backwards here? Where would I be at? I'd be at 4, right? And my x would be at 0. So it's this. It's if you started at 0, then this would be, so this would be plus 4. Does that kind of make sense? Let's put some numbers in for a second. So if I was looking for, let's say, this 8, right? If I was doing this one, so I put a 2 in there to see what I get out. Well, then I go, okay, y is equal to 2 times 2. I'm going to put that 2 in there, right? And then plus 4. The plus 4 is like where we started. We had 4 at the very beginning, right? So when x was 0, when we had nothing, we had a constant amount of 4. And then after that, we're going to multiply the number by 2 every time. That's what's happening there. Okay? The other thing you can do is just try it out, right? So I gave you this method of like going backwards to be like, okay, that when x is 0, that is going to be my constant, like, you know, what I add there in the end. But what we could have done, right, is let's say you had a table like this, and we were looking at this one. So I said, okay, y is equal to, I know this thing goes up by 2 every time, so it's going to be 2x, but I don't know what I need to add or subtract here to make it work out. So then you can actually just make it work out. We can go, okay, 2 times 3, so y is equal to 2 times 3, and then how much more would I have to go to get to 10? 2 times 3 is 6.
4.
I got to go 4 more. Right? Maybe you like that method better. You should. They can both work. Let's do it for the 4 too, just to set that in. So let's say we had y, come on, pen. Y is equal to 2 times 4, right? So 4. And then I don't know what I need to add or subtract yet, but we can figure it out, right? 2 times 4 is 8. How much more do I have to get to get to 12? 4, right? So my answer must be 2x plus 4. Okay, I know it's a weird one. Every year this is always kind of a tough concept, but I think it comes with practice. We'll practice this a lot. Let's do some examples. All right. So on this one, guys, I don't have you creating your equation on this one. All we're doing is I'm going to have you guys put in the answers for this. So it's saying if we had the equation for the first one, p is equal to 7n plus 7. It's just saying what is p equal to when n is equal to 4. Does that kind of make sense? So if n is equal to 4, that means that we're going to put, come on, pen, you can do it. We're going to put a 4 in for n. So this would be like p is equal to 7 times 4 plus 7. Okay? So you'd actually just put that into your calculator and figure out what you get out. So that's the idea here, right? When we're doing these, that we have an input of 4 and we want to know what the output is. So here, I'm going to open it up to you guys to do on your end, and we'll see how it goes here. Okay. So let's move on to the next one there. So, all right, this is a good one. So back to our patterns, right? So these will actually be like questions that you guys are going to have in your homework in a second here too. So it says here's a pattern of triangles made with congruent toothpicks, and the pattern would continue on forever. Now it says write an equation for the number of toothpicks t in figure n. And they've just kind of given us a blank. I'm going to get you guys to do this in a second, but the way this is going to work is if it says write an equation for the number of toothpicks, then that means whatever my answer is, it's going to be t is equal to, and then some number, so it'll be like 4, and then the figure number n, so that would be like, so then you'd write n, and then maybe like plus 5. Something like that, right? So when you guys type this in, it'll look like that. You should have like a where you can type in a t, an equal sign, a 4, an n, and a 5, right? You can type that all in. That won't necessarily be the equation, right? But to get you guys going, what the equation will be is, well, you know, a good place to start here would actually be like to write down like that table like we had before. So if the figure number here, so if like our n is our figure number and our t is the number of toothpicks, then our n is like our input and our t is our output, right? So let's actually just throw some of these numbers in here. So our n, so figure number, so far we have 1, 2, 3, and 4, right? That's what we have there. And then we can start to get a sense of this if we say, okay, figure number 1 has 3 toothpicks. Okay. Figure number 2 has well, those 3 and then another 2, right? So it has 5. And then you could probably get the pattern from here even, right? So now those 5 and then another 2. So that's going to be 7. And I probably don't even need to count this one. This one's probably going to have 9, right? Do you see the pattern there that these are going up by 2 every time? All right, so I'll get you started on this. Your answer here is going to be t is equal to, and then this part here tells us that it's going to be 2n. Come on, pen. You can do it. 2n. But then that won't be quite right yet, right? Because if I go 2 times 3, right, that's not going to get me there. So it's going to be 2n, and then it's going to be plus or minus something else, okay? So I'm going to leave it there. I'm going to let you guys see if you can figure out what that something else would be. So I'll open it up to you. All right, so yeah, since this is a multi-part question, that didn't work out so well on your guys' end. But so if we do this one, just check your work with mine there. This would have been 2, or t is equal to 2n. And then do you see, like, if I took, I'll show you both ways to get this last part. So if we had, well, just even throwing a number in there, right? If I go 2 times and then just try out some different values for n, right? So if I tried out 3, right? So 2 times 3 is 6. How many more do I need to get to 7? Well, I need 1 more, so plus 1. Right? And that would work for any of them. I could have chose the first one too, right? I could have said, okay, 2 times 1, right? If I would have thrown this one in. 2 times 1 is 2, and I need to add 1 more to get to 3. Okay, so you can do it that way. The other way we can do it, though, is we can go back one step, right? So what if I went down to 0, right? So if I went down to like figure number 0, well, this would go down 2, so it goes back 2, and I'd be starting at 1. So when n is 0, our t is 1. The reason why I'm showing you guys this method is this is really going to come in handy when we start graphing these things. It's going to make a lot more sense. Like there'll be a big connection there. I just want you guys kind of being like having the concept of that for now, okay? So anyway, so if we do that, it should be 2n plus 1. So let's see what we get. Yeah, we're right. All right. So now the next part says determine the number of toothpicks in figure number 33. All right. So here is why making an equation was an advantage, because there is no way that I would want to draw out all these figures, right? But luckily I don't have to anymore because I have a handy equation that we just made, right? So what we're going to do, erase this for some room here, is we're just going to be putting in 33 in place of n, right? Because n is our figure number. So now we can just write out t is equal to 2 times n, which in this case would be 33, and then plus 1. So then t would be equal to 2 times 33 would be 66 plus 1. So t is equal to 67. All right, submit that part. All right, now getting a little bit trickier now. Now we're gonna bring in the tough stuff. So this one says which figure has 21 toothpicks? All right, so when it says which figure, remember what we're looking for. It's saying like what's the number for n has 21 toothpicks. So let's write out our equation again to see if we can make sense of this. So it says t is equal to 2n plus 1. And they said, oh, sorry, never mind. I was really playing that up. This is just the same as the last question. All we got to do is the same as the last one. So which... Oh, no, this is wrong. Yeah. Okay. Sorry, guys. I'm confusing myself. So which figure number has 21 toothpicks? So again, now, yeah, we're looking for n, right? But this time, we actually know the number of toothpicks. So what we can do, we know that t is equal to 21. So what I'm going to do here is I'm just going to put in what I know. I'm going to say, well, t is 21. So instead of writing t, I'm going to write 21. And that's equal to 2n plus 1. Now, you're probably seeing why we were doing all that algebra stuff in the last lesson, right? Because we're after n. So we need to do a little bit of rearranging here to solve for n. Okay, so I just need n on its own. I don't care if the n's on the left side or on the right side, so I'm just going to leave it over here. And which one do I get rid of first, the 2 or the 1? If you guys remember from last class.
You had -1 off of both sides.
Yep, perfect. Yeah, we get rid of the 1 first, right? And I think about it as the 1 is like less attached to the n, right? It's on the outside. It's like easier to take away. Yeah. So and then you were correct that we would subtract that, right? You always do the opposite of what's being done. So it's being added, so we have to subtract 1, and then we have to subtract 1 from both sides, right? That's always the case. So those cancel. So now we have 21 minus 1 is 20 is equal to 2n. And then the very last thing we'll do here is just divide both sides by 2. And sorry, the reason why we're dividing is because we were multiplying, right? So opposite of multiplying is dividing. So divide by 2, divide by 2. And I ran out of room here. So I'm just going to write it over here now. But our answer in the end would be 20 divided by 2 is 10 is equal to n, right? Or n is equal to 10. It doesn't matter which way it's written. So that should be right. So now let's try that. So then we type in 10 for our answer. And we were correct. Now, the second part there said, how could you check your answer? Any ideas how we could check if 10 actually was the right answer for n?
It would go 2 times 10 plus 1.
Nice. Yep. Yeah, so we can try putting it into the equation again by saying t is equal to 2n plus 1, right? Just the equation that we had. And then we could say t is equal to, and then we'll put 10 in place of n and see if we actually do get 21 out. So then we'll go 2 times 10 plus 1. So that's equal to 2 times 10 is 20 plus 1. So t is in fact equal to 21. All right, let's try a couple more. Okay, yeah, I'm gonna let you guys do this one. Give you the example there. So it says there are 12 Sour Patch Kids in a bag. When you start eating them, you eat 4 Sour Patch Kids every 2 minutes. Determine each statement about the number of Sour Patch Kids is true, or whether each statement about the number of Sour Patch Kids is true. Okay, so it says the first one is the initial amount of Sour Patch Kids in the bag is 12 candies. Okay. The second is the amount of Sour Patch Kids in the bag decreases by 2 candies per minute. And then the amount of Sour Patch Kids in the bag after 4 minutes is 4 candies. All right, so I'm going to pause here. I'm going to let you guys just answer yes or no to these, and then we'll go through it, okay? All right, let's see how you guys did. And all right, pretty okay. I didn't really give you guys much info, so you guys did pretty okay. All right, let's kind of go through this and see what's happening here. So I'm just gonna read it one more time just for so we can get our bearings here. It says there are 12 Sour Patch Kids in a bag when you start eating them. You eat 4 Sour Patch Kids every 2 minutes. All right, so let's actually make a little table here to kind of get our bearings. So if we made a table like we had above, and this time what it's going to be is the number of Sour Patch Kids, right? So this will be, we'll call that maybe like our candy. That'll be like our output. Okay? Let's call it Y. Usually it's Y. Okay? And it says that you eat 4 Sour Patch Kids every 2 minutes. Okay, so this will be like minutes will be on this side. So that'll be M. Okay? You know what? If we're going to use M instead of an X, let's use like C for candies. So this will be our minutes, and this will be our candies. Okay? So in this case, if we kind of drew this out, right? How many candies would we have after, and let's even start with 0. After 0 minutes, how many candies are in the bag?
12.
Yeah, we start out with all of them, right? You've got 12 in the bag, so there's going to be 12 at 0 minutes. Okay, now it might be a little bit tougher, so like at 1 minute, maybe I'm not so sure, we will in a second, but after 2 minutes, do you guys know how many would be in the bag now? If you eat 4 Sour Patch Kids every 2 minutes?
8. Oh.
Yeah, right. You're eating 4, so you eat 4 every 2 minutes. So now we'd have 8, right? Anybody have an idea what number we could fill in there after 1 minute?
10.
Yeah, it'd be 10, right? And you're probably starting to see the pattern here that we could keep going with this, right? After, 3, 4, and 5, this would be, 12, 10, 8, 6, 4, 2, and then after 6 minutes, looks like we're out of candy. Okay, so that's kind of what we have going on here. So now let's just kind of look back to our the initial amount of our Sour Patch Kids. So you guys all did well on that. The answer for that one would be yes, right? We started off with 12. Okay, and then the amount of Sour Patch Kids in the bag decreases by 2 candies per minute. Do you guys see that? For every minute, for every 1 minute, yes, it does decrease by 2 candies, right? It goes down by 2. You'd be like -2 on that one. So another minute goes by, we go down another 2 candies. So those ones can be a little bit tricky, when they give it to you, the question as, 4 Sour Patch Kids every 2 minutes instead of every 1 minute. So sometimes you guys are going to have to fill that information in, right? All right, so we have that one. So in that case, that would be yes. So then the next part says the amount of Sour Patch Kids in the bag after 4 minutes is 4 candies. Okay, so just making the table, yeah, you could figure out that after 4 minutes you'd have 4 candies in the bag. All right, and my screen's frozen again, so there we go. Okay. For good measure, why don't we make an equation out of this too? I want to show you that we can make an equation out of this one too. So we can say C, right? This is always going to be my output will be the second one, and my input will be the first one. So C is equal to, and then this thing is going up by 2 every time, right? Well, actually it's going down by 2 every time. So in this case, this is going to be -2 n. Okay, -2 n. And then what will my number on the end be? Anybody got 12? Yeah. Yeah, good job. Yeah, it'll be 12, right? Yeah, and that'll always be the case when that's where we're starting from, right? We start with 12 candies, so it'd be plus 12. So you can think about this like before any minutes go by, like before any of that happened, we started off with 12. That was our constant term, right? That was there no matter what. Okay? So yeah, it'll be 12. And again, you could try it out. Like these ones get a little tougher with the negatives though, right? But you can try it out to make sure it works. If I threw in, let's say for, well, I'll do one other than 2. If I put 3 in, right? Let's see if this actually makes sense. So if I went, the number of candies is equal to -2 times 3 plus 12, and this should equal 6, right? That's what I'm hoping for. So C is equal to -2 times 3 is -6 plus 12, and yes, that is equal to 6. So our equation holds true. Okay, let's... Okay, I think this is the last one, right? No, there are 2 more. Okay. Okay, so let's do this one now. Okay, so in this one it says a town's population has been growing linearly. So that means like going up by a constant amount. In 2003, the population was 26,000. The population has been growing by 1,200 people each year. And then it says write an equation for the population P in X years after 2003. All right, so I know this one is really wordy, and you're probably just saying what, but it's not as bad as it looks. So, in 2003, the population was 26,000, right? So if I want to make, let's just write it out first. Like I know that it's going to be, the equation will be P is equal to something X, and then it's going to be like plus or minus something, right? Now, I've been talking about that constant term, right? It's like where we start. That's going to be the plus or minus something, right? So the plus or minus something, that's where we started right here. That was the population in 2003, like at the beginning, right? So I know that in my equation, this will be something plus 26,000, right? That's where we're starting. So even when X is 0, we still have 26,000. Okay? Now, what is my... What's that number going to be in front of the X? Anybody know?
1,200.
Nice. Yes, because it's going up by 1,200 every year, right? So if I could make a table of that and we could show, but yeah, I'm hoping you guys kind of see that. So that'd be 1,200, right? And there you go. So that would be our equation. So we can type that in. So we'd have 1,200x and then plus 26,000. Okay. Now it says use the formula to find the population in 2009. Alrighty. So the question is, so we want to know, using this formula, we want to know what P is in 2009. Okay. What number would we put in for X?
3.
So 3, where do you get 3 from?
He means like there's 3 years in difference.
3 years in difference? Well, so this was right, yeah, so this was 2009, right? And just remember, we started in 2003. So really, we just need, here we need to go 9 minus 3. Right? So there's going to be 6 years have gone by. Does that make sense? So then in that case, we're just going to be putting 6 in here. That's the number of years that have gone by. So 1,200 times 6 plus 2,600. Okay, so maybe we'll just do this one together. I'll just put this one in. So this was 1,200 times 6 plus 2,600. Okay, so we get 33,200. Oh, and I don't have the ability to try that one more time. 33,200. Hey, we got it right. How are you guys doing on that one? Are you guys kind of following this? I know it's a new concept. It's a It can be a tougher one. All right, last one. Last one, and we'll save it. We'll make it like an easier one too. So, okay, so this one says the height of a certain plant can be modeled by this formula. So h is equal to 4t plus 7, where h is the height in millimeters, and t is the time in days. All right, so which of the following best describes the dependent variable in this model? All right. So you know what? I find the second question says, which of the following best describes the independent variable? I almost find it a little bit easier to do this one first, right? Because the independent variable is the one that doesn't depend on anything, right? It's the one that just keeps happening no matter what. Okay, so in that case, what would our independent variable be? And I only really have two options. It's going to be either, well, I guess they have it kind of funny, but so our independent variable in this case would be, well, that's going to be our t, right? So as we put things in for the time, then our h comes out, right? So what would that be? So the independent's going to be time t. So the time t is the input or independent variable since it causes the height to change, right? Yeah, this is the one that causes it to change. And then our dependent variable is the one that depends on it. So the h is the output or dependent variable since it depends on the value of t. Does that make sense, guys?
Yep.
Yep. Okay. Perfect.